Stars are giant balls of gas millions of miles away. But how do they form? What happens to them? Every single star you see in the night sky goes through a life cycle, and today I'm going to tell you about it. Hi, I'm Suzanne Eisenberg, a junior docent at the New Mexico Natural History Museum, and today I'm going to talk about the life cycle of stars and show you how they're classified in an HR or Hertz vessel diagram. Before we get started, I made free handouts that you can use during this presentation. One of them is for labeling the life cycle of big and small stars, one for astronomy terms, and one for labeling the HR diagram. I find that the ones for the big and small stars and the HR diagram really helps translate the presentation into a cycle, but you can also use them to make your own. So before we start off, here are some terms that might be useful for measuring things in astronomy. If you want, you can also use the astronomy terms handout. So the first one is Kelvin, and this is a scientific unit of measurement, specifically temperature, that's used in astronomy. It's used because it's considered a universal constant, and it translates about 0 Kelvin to negative 459.67 Fahrenheit or negative 273 Celsius. And here are the precise formulas if you want to use them. So in order to measure mass, or how big things are in astronomy, we use solar masses, and this is basically just like the mass of our sun. So solar mass is 1.4 times 10 to the 27th cubic meters. To put that in perspective, 1.3 million Earths can fit inside, and it's 330,000 times the mass of the Earth. So another important thing to know is how exactly they're classified, and they're classified in an HR diagram. So the HR diagram is based off of two things. It's based off of the luminosity, which is the surface area times the temperature, and also the temperature at the bottom. A few things to note about this graph is that the temperature actually increases as it goes to the left, which is different than most other graphs. And another thing to note is that stars that are hotter tend to be more blue, while stars that are cooler tend to be more red. And this might seem confusing at first, but if you think about something like a match and a flame, the lower part of the flame that's blue is hotter than the part of the flame that's red just above it. So that's kind of the same with stars. And so when a star is born, it goes on this kind of line in the center here called the main sequence. And this is where about 90% of stars are. So let's start out with the low mass star cycle. And for the purposes of this presentation, this is going to be about less than 8 solar masses, or less than 8 times the mass of the sun. So they start off with a molecular cloud. And this is basically a bunch of gas and dust. And what happens is, because there's a lot of turbulence in this cloud, it begins to clump up. And as it clumps up, it begins to gain heat and it begins to gain mass. And this becomes the core of the star. So it gathers all of the gas and dust next to it, and eventually it forms a full star. So you may be wondering what happens next. And this is where we have our two types of low mass stars. So this is the second step on the sheet for the low mass stars, and there are two ways this can happen. One of them is a brown dwarf, and this is basically any star at less than 8% the mass of the sun. And these stars don't have enough mass to ignite, basically, so they stay kind of unignited and eventually cool down. The second option is stars that are more like our sun, and this is basically like 0.4 to the upper limit of 8 solar masses, and these are able to ignite and continue in the star cycle. So you may be wondering, well, what does a star do? Stars do something called fusion, and this is how they get their energy. So there's kind of a long, complicated formula over here, but basically what happens is they convert hydrogen into helium, and this produces energy for the star to exist. A star is able to be considered alive as long as it's, and on the main sequence, as long as it's forming hydrogen into helium, and it's able to continue being a star as long as the energy from the fusion is not outweighed by the energy from the gravity pushing down on it. And that's called hydrostatic equilibrium. Okay, so on an HR diagram, our sun would be roughly in the middle, and this is where the medium type stars will be. And you can see it's not especially hot, and it's not especially luminous, but it's not as cold or dark as the stars toward the bottom. So the next step is, after 100 billion years, the star eventually runs out of hydrogen to burn. And after this point, it starts burning more and more less efficient elements in order to get energy. So it starts off with burning helium, and then it gets more hot and dense. And after about it reaches 100 million Kelvin, the helium then fuses into carbon. So it kind of goes down this cycle of helium, carbon, neon, oxygen, silicon, and then iron. And when it gets to iron, the iron is a lot heavier than these other elements. So it's no longer able to fuse this for energy. And this is when it loses its balance or hydrostatic equilibrium. So looking at the HR diagram again, you can see that the giants are less hot than some of the original stars, but they're a bit brighter and they expand in radius. So for example, red giant would probably be about 100 times the radius of the sun. So when the gravity can no longer hold these outer layers of the star when it loses balance, they eject into space, leaving the core. And this ejecting into space is called the Planetary Nebula and is the fourth step in the cycle. So you can kind of see that it glows a bit, and this is due to the ultraviolet radiation ionizing the gas. And it also has the core of the star still inside, which you can kind of see in this first image. So after a while, the Planetary Nebula starts to let out a donut-shaped cloud of dust and gas from its equator. And after a few million years, it cools down and disappears, leaving a white dwarf. And this is the fifth part of the cycle. So the white dwarf is basically what's left over of the core. It's roughly the size of Earth, but it has the mass of the star. It starts out at a temperature of 100,000 Kelvin, emitting ultraviolet radiation, but eventually cools down. And when it cools down, it would be called a black dwarf, but this is still theoretical because no stars have existed long enough for this to actually happen. So the white dwarf is in the kind of lower area of the HR diagram. It's still pretty hot though, and so it's kind of more over to the left. So most of the time it just stays a white dwarf, but sometimes something a little more interesting happens. And this is kind of like an optional sixth step where the white dwarf turns into what's called a type 1 supernova. And a supernova is basically a big explosion in space. So what will happen is if this white dwarf is next to another star, sometimes it will sort of start to like steal the hydrogen from the other star. And this hydrogen will cause it to reignite. So once it gets about to a mass of 1.4 solar masses, called the Chandrasekhar limit, it'll kind of like have too much mass and begin to explode into a type 1 supernova, or a type 1a supernova. And you can kind of see an example of the G299 over there. So this often happened in systems with binary stars or two stars next to each other. So now we're on to the high mass star cycle, and this is stars that have masses of more than 8 times the sun. So they start in a lot the same way with the molecular cloud. So they have a molecular cloud that has a lot of turbulence, begins to clump up, and then it eventually gets more dense and more hot and becomes the core of the star, dragging in nearby gas and dust. It goes through the same part of fusion where it fuses hydrogen into helium, and it has the same thing with the hydrostatic equilibrium of the energy from the fusion needing to outweigh the gravity pressing down on it. One thing to note is that it burns through hydrogen a lot quicker because it takes a lot more in order to sustain itself. So after that, the second step is a high mass star. So these tend to be more blue and more hot, but they also tend to burn out more quick. An example of this would be our sun has a lifespan of about 10 billion years. But if we had a star 20 times the mass of our sun, it would only last for about 10 million years, which is about 1,000th the lifetime. So yeah, so these are the high mass stars. And if you look at them in the HR diagram, they tend to be kind of towards the upper left area of the graph. So the third step in the process is similar to the third step for low mass stars, and this is a red supergiant. Now the main difference here is that they are a lot bigger. So for example, a red supergiant is typically 1,000 times the radius of our sun. To put that in perspective, if Betelgeuse, a red supergiant, were at the center of our solar system, it would extend all the way to Jupiter. So these go through largely the same process that the other ones do, from hydrogen to helium to carbon to neon to oxygen to silicon to iron. And so if you look at the HR diagram, the supergiants would be kind of at the upper center to right area. They're not quite as hot as the stars that they came from, but they're still pretty bright. So this time, when the star gets to iron, it causes a much bigger reaction. So when the core gets to about 1.4 times the mass of the sun, the Trange-score limit, the core collapses in on itself, and the force is so strong it basically pushes everything else outwards, creating an explosion. This is what causes type 1b, type 1c, and type 2 supernovas. So supernovas are the fourth part of the high mass cycle, and they're actually kind of a way that the cycle repeats itself, because when the supernova happens, it spits out a whole bunch of new material, which leads to the formation of more stars and more planets. So the fifth step can happen in one of two ways. It either happens in the form of a neutron star, if the star is between 8 and 20 solar masses. So it'll become a neutron star, and this is basically 1.4 times the mass of the sun in about 12 miles. So imagine like the mass of a star inside of the size of a city. So if you picked up a sugar cube sized piece, it would weigh 1 billion tons. Most of these actually go undetected, but some emit radiation in the form of regular pulses, such as pulsars. And there's another type called magnetars, which are detected via its magnetic field 1,000 times that of the Earth. So finally, the other thing that can happen is in stars that are about 20 to 30 times the mass of the sun, it can become a black hole. And this is a region in space that's so dense, nothing, not even light, can escape. The picture I have here is actually the first image we ever got of a black hole, taken just last year in April. Now, if you want to learn more about this fascinating phenomenon, you should check out our black hole virtual visit. So let's review real quick the life cycle of the stars you learned in this presentation. So for low mass stars, it starts out as a molecular cloud. Then it goes to be a low or medium star. Then it becomes a red giant. Then it becomes a planetary nebula, and then a white dwarf. And occasionally, if it's next to another star, it can become a type 1a supernova. If it's less than 0.08 solar masses, it becomes a brown dwarf. So, and this is the life cycle of the high mass star. So you have the same thing with the molecular cloud. It becomes a high mass star. It becomes a red supergiant, which is quite a bit bigger than a normal red giant. Then it becomes a supernova type 1b, type 1c, and type 2. And if it's 8 to 20 solar masses, it becomes a neutron star. If it's 20 to 30 solar masses, it becomes a black hole. And briefly, the HR diagram. So this is basically how you'd read a HR diagram just kind of at a glance. You have the high mass stars up here, kind of by like the upper left. You have the medium mass stars in the middle, and then you have the low mass stars by the right and down. And then you have the main sequence, which is basically like where all the stars that are forming hydrogen into helium are, and are 90% of all stars. You have the giants over here, slightly above the medium stars, slightly above the center and to the right. You have the supergiants at the top and to the right, and you have the white dwarfs that are kind of like at the bottom and a little bit to the left. So here are some references I used for my presentation. Shout out to my astronomy C&M teachers and the classes I took there. It helped a lot with this presentation. And have a stellar day.